Hey,
That worked. Yeah, we may have this happen a little bit more. Well, welcome to the June meeting of the Radio Astronomy Software or Special Interest Group.
hey.
And we're going to basically concentrate tonight on some of the projects that we've been working on across the months. So Vince sent me an email a couple of days ago saying that he was ready to discuss some of the things with the project he's working on with the Cantenna design, the improvement of the Cantenna design. But before we get started, is there any questions that you have about the special interest group, your projects? Nope.
Nope.
Vince,
You
how's your Cantenna project doing?
well, like I said, I lost my calibration stuff for my VMA, so I couldn't get on and get some measurements. But let me get on here. Okay, I'm gonna play this. Now, how do I share a screen?
There should be if you look at the bottom of the screen about midway, there should be something that says share.
Okay, let me get back out of that. Okay, hold on. Oh heavens, I lost everything here.
Oh, believe me, I understand.
Okay, mute that versus share. Share settings. Boy, there's too many options here.
I know that's what I'm thinking too. I'm seeing the same thing from my end.
Okay,
Lots.
let's see when I switch over to the PowerPoint. Uh, you guys seen anything?
No.
Let me call my wife in here. Hey. Okay, well I have my screen up.
Okay, then over on the Zoom application,
Yeah,
if you
this
look
is
at the bottom of the Zoom application, where it says audio and video and so
oh,
forth
that's the
in
screen reader.
chat, there should be a button down there that says share.
Yeah, I saw it. I pressed it, but it's all it said was share settings.
You need to go on the Zoom. Go on the Zoom.
Okay,
Now,
I'm
now,
here.
now, go down to the bottom. Now, to see, is there a thing that says share screen?
Share.
And
Okay, there
yeah,
it is.
yeah.
I see it.
Okay, so click on what you want to share, and now click share. Now it should work.
Now you
That's
guys
wor
seeing something?
that's working. Yep.
Okay. Okay. A while back, I showed some charts and I've been working on it on how to measure it. Unfortunately, I mean, this was a very confusing chart, and uh, sorry I showed it, but basically, it's how I would set up a CAN antenna to enhance the detection of the H1 line. And since that time, I've been changed a few things, like I'm not using RG6, I'm using RG 174 and 316 and a bunch of other things. In progress, just to let you know, way back in the early 60s, I actually tested, modified, and designed and built microwave antennas for fused aircraft. And then I made a mistake of solving a intelligence, not intelligent problem, and I got whisked away from the hardware world. So it was for a long time. So let's go back and look at the right-hand circularly polarized wave, which is right-hand circular polarized from a photon, and H1's coming from a photon. Let's see, I think I need to change the screen size here. Is that a little better?
Yes.
So anyway, if you look at an H1 line photon, it lasts about 200 microseconds. So if you count it out, it's roughly 300,000 cycles of an H1Y. So you get plenty of signal coming in there. Now, often just watching this, here's a one cycle. It can be also one wavelength, the distance between these two peaks, the time interval, 1 over the frequency, the phase, 0 to 360 wraps around here and come back. And then, so it can be either 360 or 2 pi radians. I'm going to use that. Now for the
Say,
H1,
I've got a question, Vince.
yeah,
You know about this right versus left-hand circular polarization. So if I put myself down at the one end and I'm looking in the direction of travel, wouldn't
yeah.
it make more sense to be clockwise or counterclockwise?
Well, they don't do that anymore because the kids don't know how to do clockwise or counterclockwise.
Okay.
Okay, but it's oh, here. I
See,
don't
the
know if
right
you can
hand
see
is
my other hand,
clockwise.
but it's right-handed, goes that way. And fortunately, with the way you set it up, if you mess up, all you have to do is change one cable. So, so the H1 line, lambda is 21.1, and this time is zero point 0.7 nanoseconds. That's the time between peaks. So I started looking into that. And so, okay, now let me look at two different orthogonal uh, probes, not just one probe, but orthogonal probes. So if you look at it, and I'm looking at it coming at me, so it's right-handed, and I'm using phi as this, and the direction is normally phi is counterclockwise, but I'm going to use it clockwise just to confuse you. Here's your rotation direction, so here's the peak, here's the tail, positive or not, at delta t over 4, or 0.7 over 4. The thing is rotated over here. Oh, why is that still there? Uh, and so mm, A is getting the signal. Here, B is getting the negative signal. A to a negative signal, B, and vice versa. So this is sort of what it looks like. We start out the blue curve. It comes like this, and it comes like that. And the B curve is going like this and coming down and coming up. So if you look very carefully, uh, this essentially, well, this is lagging. The green is lagging that. So we'll show what we do and how to accomplish it. So with two probes, well, a single probe, this is what you get. This is your power equal to some constant times this. And just for a reference point, one probe is going to be 1. Now, if I use two orthogonal probes, the output, of course, one is a sine and one is a cosine. If you go back here, this is pi over 2 apart, so it becomes a sine. Or like some people say, sin. And here's your power and your relative uh, power. And this is how it looks: up, down, up, down, up, down. And it's go relative power is 3 dB. So if you add a second probe, orthogonal, and just tie them together, you're going to get 3 dB improvement. Well, that may not be worth it. But let's look real carefully here. Let's take this blue wave and delay it. And so we just delay this guy. So we add them up. This guy has slid over to here, and we get a curve like this. And I put this magenta in there because that happens to be the color combination of blue and green. And if you look at the power, we get this, and the relative power is 4 or 6 dB, and that might well be worth it. See, which one am I on? So, and theoretically, we can obtain 6 dB improvement with this scheme, which is the same as doubling that hole size in there, that. So now I need to verify this with some testing. So I built a test bed. I'll show it to you. Our objective, how difficult is this scheme to implement for the H1 in a CAN antenna? And is it worth it? Like, how much skill is needed? Do we need some guy with an antenna background at a machine shop, or can someone just do it? Uh, are the measures easy and straightforward, or are they hard? This is the big one, cost and availability of parts. What tools do you need? In addition, you need a VMA, nano VMA. Is that adequate? Maybe you need a stronger VMA. I don't know, but this is what I'm going to try to find out. So I built this thing, and this was challenging. Number one, after 60 years, I'm sort of out of practice. I don't have a proper antenna chamber, and I looked at the price of absorbing material, and straight on, it's very expensive. I've been thinking about checking people that install these antenna chambers and see if I can get some scraps. But otherwise, I'll just have to live with that. I mean, all this is the proof of principle. So, I mean, it can be off if I see a great that.
Say, Vince,
Yeah,
what's an antenna chamber?
antenna chamber, it's called anechoic chamber. It's a room, and they have absorbing material all around it, so you don't get waves bouncing off the sides of this chamber, screwing up your measurements. And we actually had two at Hughes Aircraft. I mean, you want to hear a funny story? All of a sudden, when we're looking at, we had two different things happen. One is all of a sudden we're getting all this signal, all this interference. And so we looked at it and looked at it, and all of a sudden we noticed the beat was about 60, 70, per minute, about 1 a second, timer off. And so finally we got a diode and an earphone, and it turned out we had a new 50,000 watt rock and roll station open up about 10 miles away. So we ended up buying a whole bunch of filters to get them out of the way. And so, and way back when I was at Hughes, I had a sharp mechanical engineer and a machine. Now myself, when I hit about 82, 83, I said, okay. I thought I fixed all those. I got rid of some of my junk and all this, so I mentioned that, and some of my tools. Well, mistake. I have eyesight issues, especially with near vision. I had a retina detachment, so when I get near vision, I have no very little depth perception, and believe me, that causes issues. I no longer hop around the store easily. I have a walker to get around with, but I used to go bounding around Home Depot or Lowe's or one of three different Ace Hardwares to find what I need. So I had to go to online, Amazon mostly, and other places, and see what kind of parts they had that I might be able to use and how I might. And I went through a lot of parts, and by the time I got some, oh, I don't need those anymore. I'm still learning the idiosyncrasies of the nano VMA. Way back then, I had the equivalent of a pure VMA, only cost about $30,000 then. We work with a company with money. I had to figure out a way to generate circular or right-handed circular or right-handed test waves. Now, I had a choice of an antenna. One was cross dipoles, another was a helix. I chose cross because I said, well, I don't need the wide bandwidth of helix, except it finds out that the cross dipoles is far more difficult to tune precisely. And I'm going to look at next for a helix antenna. And so I don't have to tune and keep clipping away. That's very sensitive to make sure you get a right-handed circle using that. Uh, often they're often printed circuit boards. I can't use that. I don't have the facilities. They not only use cross dipoles, but they actually use a circular pattern and some others. I had some way to figure out how to mount the CAN antenna. I was going to do it vertically, but then uh, oh, I had the dipole in front of a quarter wave plate, a plate quarter wave back, and I was having trouble separating out the reflection from that and the antenna pattern. But I went ahead and built one. It took a while. It took a lot of frustrations. And I went through my list of about 20 swear words many times. And to do this, I actually went through about 6 iterations. One case, I couldn't get two cases, I couldn't get the cross dipole to work and tune it fine enough. I had used a tube and I couldn't prune it fine enough to get it at the H1 wavelength. I used 14 wire, that didn't work either. I tried mounting it on some ABS port, and I made a mistake there that I got so close, but I mounted it on some plastic rulers, and I drilled the holes, and I had room to do it and mount it. In fact, lo and behold, there it is. Here's my reference dipole, the green one, and this is the blue one that we delay, so that's front and this is back. If you notice, the dipole, it's oriented that way, and it's oriented that way, and so the delayed one, that's the turnstile back here. In case I ever want to put a reflecting backlight, I actually put these little stubs back here. Just a mount here. There's the CAN antenna under that. You see one of the holes there, and that's an issue. I finally found a Gorman I could put a probe in. I put it on the skin. It shorts out. And there's another one, 4 of them around this, and I can put Gormans and I can test. And I plan to test what the output will be for each one of these. This setup could be somewhat orientation specific. So I mounted it back here. I took a PCP plumbing union. Couldn't get those easily when I lived in Alabama. I don't know why. But this way I can detach this CAN antenna and work on it, and I can rotate it easily. And this goes back here. This distance is about 40 centimeters, far beyond the Fraunhofer field that you need to avoid to have near field stuff. Now you show this on the floor here. When I use it, I have a higher table and I don't have nearly as much, I hope, reflection. And there's not going to be a lot of radiation down here coming back up this close, I don't think. But we'll find out. Maybe next time I'll have that. So that's what I came up with out of PVC. I'm definitely not going to go into PVC furniture building business after doing this. And if anyone needs half-inch PVC fittings, let me know because I got a bunch left over of that. So
I use PVC a fair amount. Could you go back just a minute to the picture? So let me run this by you and see if I'm following what you're saying. So the way to really make this work, it seems to me, has a lot to do with the delay that you've got in here, right?
yeah, there's cables here, and the forward cable delays this thing to generate it. In the 9 second, I mean, essentially 90 degrees. For RG316, that's 3 inches. So this cable going here is 3 inch longer than this cable that goes there. And this is what I'll uh, hook the S11 port of the VMA, the nano VMA to. I have the same thing going to go over here, but I'm going to use different options. Like I'm going to go all the way around with just one probe and see what one probe gives me and do that. And then I'm going to do two orthogonal probes like that with just combining them like I showed. And I will probably do the pairs all the way around. This pair and then this pair with the other one underneath and that one just to see what I have. Uh, and then I will do it with my scheme with one of the uh, ports being delayed and just move my way of pairs. And then I have plans to see what happens if I have opposing uh, probes. If you sort of forgot to do that one, but essentially a dipole, you feed it in the center out with the uh, shield going to one side of that. With a probe, you sort of feed them the same way, but you feed them from the other end. I'm not sure how that's going to work out. Uh, I'm not going to try the theoretical. Heck, the dipole theoretical was worked out by a Finnish guy only about 15 years ago, finally. Real clever. So,
Hey,
now,
hey, Vince, can I ask a question?
sure, always.
Um, I hate to say this, but I have no idea what we're trying to do here. Uh,
What I'm trying to do, essentially, is get more signal from this little baby with here. So with this scheme, if I can do it, it'd be the same as putting that funnel you have on yours twice. I'm getting the same signal. Now, if I put the funnel here, I'll get even more. And down the road, I have even more ideas. One is to put a pair of these, and even four of them maybe, and be able to track in a H1 cloud, track the hotspot. That's sort of what I have in mind. Now, whether that's going to work, do that make me making myself clear?
yeah, I understand that, but the parts on the left, your reference dipole, your delay dipole, are those
Okay, the reference
generating?
dipole, essentially that was the green dipole, the green antenna.
But you're trying to generate a signal that you're going to
It's
pick up in your
generating a signal.
antenna.
Yeah, and what it does, uh, it generates a signal this way, polarized this way. You shove it forward, and then you delay it. And when you get here, they're at 90 degrees apart. And now you have a 90-degree thing rotating this way. It's very, I could have probably done a better chart for that. But that's how the turnstile, it's called the turnstile. It was invented at RCA back in 1935. And so I tried to buy some and modify them. And number one, they didn't look easy modifiable. well, and I think the lowest price one was about $700. And so that's why I decided to make my own, and that's sort of that. But this is generating my right-handed polarization, which would mimic the H1 wave,
Okay.
and see what happens inside this can, and see if my ideas for enhancing the performance would work. Does that make sense?
Right. So your reference dipole, you're delayed. Are they radiating in 360 or 4 pi
No, no, no,
steradians?
they're a dipole, so they're rating one's ready to polarize this one, one's ready to polarize this one, and by phasing it right, you make it right circular. And if you want, I can make a couple more charts and send them to you and see how it works.
Are you using the VNA as a signal generator?
Yeah, the DNA will be the signal generator. That's going to come in right there. And then it will have to be, the other report will be out here. And I'll have a cable between those. Does that make sense? So here's your generator. So I then look at the log magnitude, the dB, of the signal coming here from here for the various conditions. And that way I can see if I have more signal with which condition gives me more signal. So I'll be comparing that. I'll also see how it works around there. These happen to be some strings because it's sagged a little bit when I build it. Does that clarify it? Do you need to?
Yeah, and just one more question then is, so your reference dipole, is that radiating like a cone out? Your circular, I know you got the circular,
Yeah, it's ready to cone out, but most of it's going to go here.
okay.
And it's radiating, I mean, I have it right at the H1 frequency.
Mhm.
And that created problems because those at that frequency, those parts are so darn small, I have a hard time seeing them and a hard time positioning them. You know, I, I guess I could have done what we done one case, I could have built one for, 2 meters and this would be huge and see if it worked there. But I actually made an H1 this way, I'll see. And so what we're going to do, Mr. Murphy's there. Mr. O'Brien says Murphy's an optimist. Somehow my nano calibration set is missing. I think what happened, it got knocked into the trash when I cleaned up the office a little bit. I didn't notice it. It's now in the landfill. So like I mentioned, I'm going to make measurements with all the different probe combinations. And then when I get all this done, I'm going to rest. And I apologize for not having results tonight, but as I say, Murphy's been there all the way with me. Uh, and
So you've got the VNA generating the signal. What's your detector? How you?
the detector is the other port. There's two ports on the VMA. You got port one and port two. Port
Oh,
one is
you're using the V.
generating. Port
Ah,
two is what you're receiving with. That's how you detect your through stuff.
okay.
And if you look, and you got to be real careful using this thing. I mean, this thing, uh, the first time I tried to measure the phase length of these things, I got twice, the phase I was expecting. So I chased that down. I mean, when you get one of those things, it doesn't, well, I don't do it as fast as I used to. I mean, it might take 2 or 3 days. Okay, this is what happened. And this is sort of what you guys can see this, it's sort of like a drill that
Yeah.
turns around. So that's it. I'm sorry I don't have more, but I mean, I am making progress and we'll see what happens. Like my wife says, it gives me something to do in my retirement. So, so we'll see if I have anything to show worthwhile next meeting.
I really like your test harness, how you built that. That's pretty cool with the PVC pipes.
Yeah, let's see. I went through 1.5 cans of PVC glue. I have a whole bunch of fittings left because I tried one of them. Oh, that's not going to work. A lot of iterations here. You know, Like Mr. Edison said, invention is 1% perspiration and 99% inspiration. And one of his other quotes was, I never make a mistake, I just find another way that won't work. And I found several ways that don't work or had problems with. So, uh, but
Well, I can
at
relate to
least I
this
can do
because
it.
I hadn't worked with PVC pipe myself until I built that dual dipole array, and I used the PVC as the masts for the thing, and also the PVC for the central insulator. So it's pretty handy stuff, actually.
Oh, yeah. And just don't get it on your hands.
Well, I mean the PVC piping.
Yeah.
Yeah, I didn't use the glue much at all, just in the central insulator. Well, thanks,
Well, I
Vince.
found if I moved this thing around too much, sometimes they were real tight, I didn't have any problem. Other problems that were loose. So the quality control people here, they're not always exactly the same. So let me clear this off the
Somewhere there's a stop, a little bar that says stop.
Yeah, it's usually
There
red.
we go.
yeah. Yeah, you just have to find out where it is on the screen.
Yeah, it reminds me somewhat of that dual dipole array in
Well,
that,
it is. I mean, the
yeah,
Jupiter thing, it's a photon down at that frequency.
and it's circularly polarized.
Now, I'm not sure how they feed it. I mean, you can feed it different ways, and it's the feed, that makes it circular or not. I mean, it's real handy because if you just have one probe, you're still going to get a signal out of it.
Yeah,
Like the reflector that Gary has, well, you'll still get a signal out of it because the thing is always rotating. But now the original can antenna was made for extending Wi-Fi signals. That was the original purpose. And there you got into the polarization. It didn't have them both aligned, they wouldn't work. I always wonder if this works if you can make two circular polarized can antennas for Wi-Fi. My brother in his farm is making one so he can extend his Wi-Fi from the small uh, little cabin they have out there out to the barn before they go in town. That's in Rochester, Minnesota. All you northern people. So anyway,
okay. Well, it sounds like this is going to be something we get updated with each month.
yeah, I'm going to keep. I mean, like my wife says, it keeps me out of trouble. Darn it.
Yeah. Okay, well, has anybody, first of all, any other questions for Vince?
Actually, I had one more, Vince.
Sure.
Your Cantana, the probe distance from the back, is that what distance did you use?
9 centimeters, a little less than 9 centimeters.
Okay.
When I was tuning the probes in there, and that's one of the things I have to find out is how much microwave network I'm going to need to make this thing work. And that's, you know, if that's where if someone has to be really technically astute in this field, then it's not going to be very pragmatic. But if I can make one that's pragmatic to the field, it's roughly 9 centimeters, about 8.9. And when I was checking the tuning of it, I could see the reflection uh, from the back wall as I brought the dipoles into resonance. And you can actually see that. Uh, and then oh yeah, and then I had couple bad cables in there, and a couple bad, couple bad connectors and all that, which I tossed. But
Yeah, I just measured
it's a
mine.
nice learning experience.
I was just saying, I measured mine as nine centimeters as well.
9 centimeters.
Yeah, yeah.
Yeah, so you have RG, it's a 316.
Yeah.
Not 174, you'd have to be a little closer.
Yeah.
So it's Yeah, well, one of the funny stories I was going to say, we had a incident happens every now and then when we had a bunch of cables lined up, and all of a sudden on the scope, we're showing the output getting there before the input did. And our joke was, heck, hook it up to the market or hook it up to the race wire. Well, it turned out the cables were mislabeled.
Mm.
And that's why we got the discussion there.
So it's another
Well,
question I
those memories are coming back from those early wild youth days.
have.
You guys are calm when you're young, right?
So the question I want to ask is, so we have this antenna. Let's say we have it. Your experimentation is successful. Could you take that design and then put it as the waveguide for a parabolic dish?
Yeah, it is used. That's often what those little can antennas are used for in some cases, or as a cheap feed for a dish.
Okay.
Yeah, so they're used for that. We can do that.
Okay. Cool. I kind of thought so. I just wanted to see what you thought.
Yeah, that's all the questions. I may have an answer. It may not be the right answer, but I may have.
So you could swap this out on your Wi-Fi antenna and start taking those measurements that you were doing.
Well, I was gonna use the Wi-Fi around the house originally, but and that might have been easier, but because there's plenty of signal around the house, you got 2.4 and 5, but I decided to go directly this way. Like I say, I'm definitely out of practice. Actually, I did do some hardware work. We're looking at a possibly unique magnetron, but
So what you do
as it
then is
turned
you
out, the
take,
theory didn't quite pan out. Someone missed the square root of -1 in all their equations.
so I'm sort of going to segue then from there into, so what you do with the signal is you take it in and you feed it into your, well, you first of all, I guess would feed it into your amplifier, the LNA, and then you feed that into your
Yeah, I'm going to feed
software,
that in,
software, yeah,
and then
your software to, go
yeah,
ahead.
no, yeah, I'm going to feed it into an amplifier. If I get two of them, I can use what's called monopoles, where you put two antennas that way and you look for the null in between. You get a sum, both of them, and then you get a null. And there's two ways to do that. And that way I hope to be able to track an H1 cloud or maybe find the hotspot. Now, whether that works, I don't know. But I mean, it's just trying.
So
Try.
after the signal gets amplified, then you're going to go into a software-defined radio. And the reason I wanted to mention this is that I'm not sure who has software-defined radios yet has dug into it. This last couple days ago, Daniel, he said he couldn't. He was writing me to tell me that he couldn't make this meeting tonight, but he mentioned that Gary, you went out and worked with him on getting some software-defined radio set up for him. Is that?
Yeah, pretty much. I don't know how. Yeah, we basically he was trying to use the AirSpy software to connect to his Cantano, and I was just kind of coaching him on how to do that. He was getting this horrific interference somehow where he was, and I suggested maybe going outside or some other place. It was whatever the source was, probably in the room that he was in. Might be a Wi-Fi router or something. But he sent me a picture later of a really nice clean signal that he was getting. So
Oh,
he was
good.
able to get the when you before you calibrate it, you get that kind of a curvy
Mm-hmm.
kind of shape to it. So he was getting that. So I was like, yay.
What software was he using? Well, you said he was using AirSpy,
Yeah, yeah. SDR sharp.
SDR Sharp.
Yeah. So basically just trying to get that up and running. So he got it working. Then I asked if he had gone outside, messed around looking at anything, but he hadn't got to it yet. So that's kind of where I think he loved it.
And Bill, I think you also have an SDR, that one you bought from some outfit down in Alabama or something.
Um, yeah, I bought before I bought my radio telescope platform that I'm currently using. I was working with Gary, and I was embracing it. I bought a AirSpy receiver, and then I bought a what they call a spy verter, which is basically a receiver that goes from DC all the way up to, I believe, about 1 megahertz. And so that's what I'm using for my space weather thing right now, is using an up converter to go into these spy air spy, and then that goes into my computer. But yeah, I'm working on using a software defined radio for the space weather thing right now.
So for those of you that don't have a software-defined radio yet, we've got a couple people here maybe that I guess I haven't heard from you. Bob or John, have you worked with the software-defined radio yet? No?
Got one. I just haven't had a chance to hook it all up. I still need to get a little bit more hardware.
Well, I was gonna put in a plug for starting working with them. I started working with them a few years ago with an amateur radio. Had nothing to do with radio telescopes, and I guess I was just gonna say they're pretty easy depending on what kind did you get, Bob? Did you say it was an AirSpy?
It's SDR. I gotta find the thing now. I haven't looked at it now.
I don't know if you got
It's the one y'all were talking about a few months back.
Oh, well, my first one was really simple. It was about the size of my thumb, and they're cheap. You can get them for like $45 off Amazon, and it's got a USB connector. You just basically you plug it into your computer, and then for an antenna, you can get away with just having, well, if you got a really close station, which I do, you don't even need an antenna. It'll pick up a nearby FM station. But if you want to work it better, even just a wire connected to it will work, and it doesn't have to be fancy. You can have a few feet of wire around your office. So to start working with them is actually very inexpensive, and then you need software to work with it, and it's free software. So you can start fooling around with these things right off the bat. And if you want to get, like initially, mine wouldn't get down into the ham bands, so I found they sell a little thing called an upverter, which will change the frequency so that the software-defined radio can pick it up, so you can listen to ham bands and so forth. But initially, if you don't get into any of that stuff at all, you just get this little software-defined radio thumb thing and plug it into your computer. You can start picking up local broadcast stations. So it's a good way to get started. And then that software-defined radios are used a lot or that technology in radio astronomy. So I just want to.
I was going to say one thing that Sandy is AirSpy sells an HF model receiver now, so you can get all the ham bands. They actually sell one dedicated for that now.
Yeah.
So, question. I don't know if you can see this little antenna I'm holding here.
Yep. We can see
Might
it.
that work? If I just screw that onto my SDR sharp?
Mm-hmm.
Screw that onto what? The SDR Sharp software.
I'm sorry. My SDR dongle. So this is what it looks like.
I've done that and it works.
Okay. I just happen to have one lying around. I have no idea where I got it.
Well, I don't
Look,
think
on my desk. How about that?
It works on the LTR SDR dongle, the $37 one, and it works on the AirSpy system.
Cool.
Anyway, they're kind of fun to play around with if you just want to play around with a little radio that
Like a tutorial session or whatever.
Yeah, something like that. Um, I've got a couple SDRs here myself. I run several software applications. I've got that where I got into that Jupiter project, I had to shift over to SDR Play for the actual receiver, and then that takes its own software to get that really running. So, but there's SDR Plus, there's SDR Play, there's SDR Connect, there's a whole bunch of different software pieces. The only thing is that if you start working with the hydrogen line, neutral hydrogen line, I believe the only one that I've seen that really comes out like with what we've been talking about is the SDR Sharp, because they've got that IF averaging plugin that gives you that nice curve that we're looking at. And I haven't seen the counterpart in the other software applications.
Yeah, there's a tool called EasyRA
Yeah.
that I started to look at it, but I actually haven't tried running it yet. And of course, I'm using that other system, Virgo. That works well too, but EasyRA seems to be supported a lot more. A lot of people talk about that in the SARA discussion boards.
They do. An EasyRA does somewhat the same thing. It'll do the collection of the signal and the graphics also of it.
Hmm.
I I installed it, but it took me a while because my Python wasn't all up to speed. It's all Python scripts that you're running. Um, so yeah, that's that Ted Klein. Ted Klein has a whole number of things on YouTube. If you look him up, he has a whole bunch. He's the one who wrote EasyRA, and he's got a whole bunch of how-to videos on it. That's kind of interesting. You know, getting into this hobby, you could spend the rest of your life and only just put a slight dent in what is going on with it. So, okay, has anybody got any particular projects they're working on that they want to discuss? Okay, Bill, how now's our turn here. Bill, Sid,
All
Bill, Sid, you
right. I
you're
will.
you're
Yeah.
going in a different direction with the whole project. Sid is the stratospheric no sudden ionospheric disturbance thing, and that supposedly is sensitive to solar flares. It's one of the things that's sensitive to solar flares, and it does it kind of indirectly. The solar flare hits, changes the ionosphere, which changes the strength of the signal that we're actually monitoring, and you see this on a graph. So and it'll hit very quickly. It'll hit within, however long it takes to the speed of light to get from the sun to us, which is about 8 minutes. So it should show up quickly. Um, Bill and I have been working on this SIDS for a long time, and it has, well, speaking for myself, it's been a challenge. And what you do is you build a loop antenna, and coming off that loop, you go into a amplifier then that you feed in through a sound card to your computer, and you have software running on your computer, and you should be seeing these spikes. Um, I think what happened is he and I have been trading back and forth sound card settings to try to get this thing working right, or the way we think it's supposed to work. And I think you went off in a little bit different direction. So would you go ahead and explain that?
Yeah. So I initially followed the Stanford's solar. They have a manual on there, and I kind of stayed with that. And yeah, so I got the SID receiver. I built my antenna, and followed the diagrams and got all that done. And the first hurdle I came into was, of course, the sound card. And So I tried the 4800, which they don't recommend. I went to 9600 sample rate and got a couple of different graph profiles. One that kind of went straight across, but with no peaks or no stations showing up. And then I got reconfigured my sound card to what I thought was correct. And then I've got this noise floor that's kind of high, but then drops off pretty quick down to another noise floor that goes to out beyond 30 kilocycles all the way out to 50 kilohertz. And so I did see what I believed to be 3 stations that were on the slope, but I couldn't really tell because the way it was apparently attenuating the noise floor of the signals. And so I thought, well, let's see if we can come up with an idea here to maybe model this and verify that we're not getting noise from something else inherent in the system or somebody else, generating those wavelengths. So if you go into the SIG manual there, they're actually doing this. What I'm doing in that is using a signal generator and actually using or generating those signals and trying to simulate or validate what is happening on your screen. And so I started at the very end of the very upstream by the antenna, and that's where I used a coil and I pumped a RF signal into a into a relay and actually generated that signal. And I sweep that band. Now, as I went higher, I started getting these these harmonics, I think, from the coil or something that was happening. So, the coil was kind of a cheap way to do things. But I was actually able to verify them on my oscilloscope and say, yeah, those are in fact it. I mean, it's true, it's definitely working. The antenna is working. There's no shorts in the antenna. Measured the resistance, and yeah, it looks good. And but the thing that I'm struggling with, I think, with like yourself, there is why the sound card or what is happening, and it's not showing the same thing that is presented on the manual or on the instruction manual, having this real nice clean valley of signals, and then showing this thing happening. So that's where I decided, well, let's try something different, and that's where I decided to get the software-defined radio, and as an alternative to that, and I think, as I mentioned, I used a receiver, the SpyVerter, which takes a very low frequency and up counts it to a higher where the air spy can see that, and then there's conversions that goes through, and then you get that on my SDR Sharp. So I went through the same deal with the signal generator, and I was able to capture a much cleaner signal, and I could see the whole band. I could sweep all the way to sweep all the way to 50 kilocycles and all the way down to DC, or down to pretty much to zero. And the noise floor was really nice. It didn't jump up or anything, and so I thought, okay, so this is pretty good. And then they tell you to kind of leave stuff on for a while, and I went and left it on for a couple of days. And the first thing I noticed is that around 19 kilohertz and 23 kilohertz, I was getting two spikes, and they were varying in amplitude. That the 23.5 was much higher, and the 19 was much lower. But during daytime, when the sun was up, those signals came up. They rose as the sun came up. And then as the sun went down, they totally disappeared. And so I'm, reading the literature here, it sounds like that is maybe a consequence of the ionosphere changing and being less reactive and more reactive as the sun goes up and comes down.
Yeah, I think the atmosphere is getting more charged.
Yeah, yeah. So I'm going to I'm on travel right now, but when I get home, I'm going to try to record that and just look for some trends and just see what it does and just see what kind of behavior I get. And if anything goes crazy high and I get something that looks like a solar flare or something, then I'll go, well, that maybe this is good.
Well, that sounds pretty good. The thing that's kind of confusing for us, at least it was for me, is that when you get this installed, the old way to do it is they give you software. And so you've got the software that you're managing that where you see the signal and it's storing these files underneath the covers that you can interrogate and bring up in that software and see if you've got any of these spikes that you're looking for. That's the old software. What I found out is that the people who are doing this, because there's a special interest group within SARA that's doing this, the VLF folks, they have a more modern piece of software. It's got quite a different interface to it. It actually is able to actually look at the GOES satellites signals to see what's happening real time, and then you can see what's happening on your system. And I have one of my to-do projects is to try to get that software in and up and running. But I still have not gotten to the point where I'm real happy with my SID results. And so Bill and I have occasionally communicated back and forth, kind of, if nothing else, I guess commiserating. But it's of the projects that they have for the Astronomical League, this one I think has been the trickiest um, to really get it working right. But I'm going to keep at it, and it sounds like you are too. So maybe what we can do is put together some pictures of stuff and maybe some pictures of what we're looking at in the software to explain what we see going on. We're not using this, well, out of the box, not the way that Bill is doing it. I'm doing it a little bit more out of the box. There's no software-defined radio involved.
Yeah.
And like I said, it's to the point where within SARA, there are special interest groups, and there's one for this, and it has been around for quite a while. So, and a forum, you can email the forum and say, this is what my problem is. And there's some real experts online. I haven't taken advantage of it yet, but I think I'm going to need to.
Yeah, I went on there a few times, and it does seem like the sound card is kind of the big thing that people struggle with at first.
Yeah.
The other thing, I read another technical paper on this subject, and not only is there, solar flares, but I guess lightning and there's other things in nature that will cause this. And so I guess the skill is to try to figure out and try to parse out what is the solar flare event versus lightning or something else that's going on. So yeah, I'm continuing to read about this a little more to figure out, how this works.
Yeah.
And so it's becoming more of a journey, but that's okay. I'm having a lot of fun doing this.
Yeah, I feel the same way. I feel exactly the same way. And it looks like to me, it can take a long time. In fact, some of the people in SARA, had theirs up and running. They look at it, fool around with it. And they've been doing this for years. So we'll keep at it. Building it is not difficult at all. Making that antenna, it takes two people to do it, but actually getting all the hardware together is really easy.
Yeah, yeah. Interpreting the data and interpreting how and what we're seeing. And that's what I'm going to do right now with I've got them both working side by side.
Yeah.
I've got the old software working side by the software defined radio.
Yeah.
And so I'm kind of looking at them both to see if they're behaving the same way. And so I'll let you know what happens with that.
I think that's the way to go. Okay, is there anybody else that has a project or something they want to talk about?
Not me.
Okay, well, we are at 8 o'clock. Let me turn the recorder off then.